let's talk about the prerequisites for this course and software requirements. Now you need some programming experience, be it MATLAB, be it C, be it Python, be it Fortran, be it Java, be it anything else. But you need to have some programming experience. If you have no programming experience, then you will not. Then you most probably will have lots of difficulties understanding the content of this course. Okay, so this is a very strong prerequisite that you have to have some programming experience so that you understand what it means by loops, conditionals like if, then else, what it means to read from a file, write to a file. You may not remember everything. That's okay. But as long as you have understood it at once in your life, then you will understand what we do in the course. Okay, so looping and so on is something that will be expected and that you already know these things, these programming skills. Subroutines, functions, how to open an editor, write a code, compile it, run it, or at least run it. So these skills are something that you should already know. You're not expected to know a particular language as such. Some basic knowledge of linear algebra is also desirable. I won't say it's essential, but desirable. So, what are vectors? What are matrices? What is to multiply a vector by a matrix or matrix by a vector, and so on? So, multiplication of matrices. So, these things I'll assume that you already know. So, if you see them and it's not clear, then make sure that you revise that or you understand these things. In scientific computing, we cannot work without learning linear algebra. Advanced ideas, not really, but simply multiplying matrices is something that should definitely know. And most important, you should be comfortable learning new software. Okay, that comfort of learning new things, as you would sit in an interview and say that I am open to learning, I am very good. It's my strong points are that I learn new programming languages quickly. Well, that's appreciated a lot because whoever is employing you or whoever is asking you to work in their lab is not going to expect you to know everything, but they'll expect you to learn quickly. Okay, or being open to learn new things. So make sure you are open. I'm sure everybody is because you're attending this class anyways. Well, software requirements, you'll need a computer. Software requirements is you'll need an OS, most probably Unix based system. You will need lots of software like Python, Fortran, sometimes some modules in Python. You'll need OpenMP, MPI, and all these languages available with you, but we don't expect you to install them on your local machine, although you can do that, but we'll give you something called a virtual machine. So virtual machine, as I'll demonstrate today, is a large file. Okay, it typically is of the size of 5 gigabytes plus. So all you have to do is you have to download a software called VirtualBox, and then you have to run that virtual machine. And as soon as you run it, many of you were already running it on their machines. It actually looks like you are in a complete operating system. So that's like an OS contained in a file. Sometimes it's called containers as well. So these virtual machines are equivalent to having a complete OS installed on bare metal, but they're not bare metal; they are files. So they're slightly slower than, in fact, sometimes quite slow as compared to a bare metal computer where you install things on the OS. But it doesn't really matter because our job is not to do things very quickly in this course, but it is to learn how to do these things quickly. So the kind of codes we'll write, they will not take a lot of time to run. So they will typically be a few seconds, or maximum a few minutes. But in the future, with the kind of skills you learn from this, they will be applicable to large or heavy duty machines. Okay, so we'll be using virtual machines for this course, but feel free to install software on your laptops. Although I don't recommend doing that right away, because sometimes you might try to install a software, a newer version, which might break an older version that was working on your machine. So start with virtual machines as we have shared with you, and then as you get more experienced with these things, you can start installing things on your local machines. But here, it's only virtual machines because you don't have installation privileges because you're not an admin to install software on these PC lab. So in the lab, you'll be using virtual machines, which will have all the software installed. In fact, to install software inside the virtual machine, that is possible because all you're doing is making modifications to a file, which is allowed. So you can run admin commands from inside the virtual machine very comfortably. There's also a third way called cloud computing, where you create virtual machines which are specific to that that environment. So, for example, Amazon Web Services, I think, is called Amazon Machine AMIs, Amazon Machine Interface. So there you have these machine files, which are like virtual machine files, which you upload and then you run it. Okay, so it's just one file in a disk that's sitting there, and then you log in through it and you run it. Just like a virtual machine, but it's specific to that hardware. It won't run on your laptop. So let's start with a short demo. So I'll be doing things typically the way you'll see a demo in the class. Now, if you want, you can follow up with this on your machines. But today I don't expect you to be doing this by yourself during the class. So I might be a bit quicker. I just want to do a demo as to what we'll be doing in this course in demo session. So as I said that we have an IIT Mandi Cloud link where you can download the virtual machine from. Many of you already have some version of the virtual machine that is there from earlier. So you can use that. The username is HPSC and the password is ME522. The file is about 5 gigabytes, but when you extract it, it becomes around 10 gigs. Okay, so you'll see something like this. I have a lot of virtual machines available. You may only have one. It's called HPSC and GB. So we have to just start it. Some settings may have to be set, but the TAs will help you next time with it. So once you start it, it may take some time to set out to run. And then once it initializes, it will look like a complete OS in itself. Okay, so let's start this demo. So what I want to show you today is, so I've opened the terminal, Alt Control T, that's a shortcut. Typically I'll be using terminal because in scientific computing, we sometimes only get access to the terminal. If you're running a code somewhere remotely, all you see is this command prompt. GUI is not available for speed or data bandwidth purposes. So what we'll do is I'll download some content from GitHub. Now GitHub, as I said, that is a place where you can maintain repositories. So we already have a repository from last year, although we'll be setting up repository for this course in the Git lecture that we do in the lecture after next. So we'll be setting a repository from scratch, and then you can clone it into your machines or wherever you want. And I'll keep committing new codes into that repository. So for today, I'll clone the repository from last time. So for that, we have something called Git. So first I'll check if Git is available. So if I do a git minus help, I get something except rather than an error. So that means it's available. So now I'll go to a folder called GitHub that I've created already. And I already cloned the repository for testing purposes earlier. So let me remove this repository. Okay. So this ls command is to list the subdirectories. In the next lecture, we'll have a bash lecture where I'll talk about these commands. But for today, I'll highlight the things you need to focus on. This is just a demo for introduction today. Let's increase the font size a bit, clear the screen, and do an ls. So there's nothing here. So now I'll say git clone. So this clone means it'll clone something from the internet that's available already. And then I have to give the path of that file available on the repository available on the internet. So this is from github.com in my repository. So my ID is gbutani, and then the repository name is HPSC underscore 2023. We'll have similarly 2024 this time. I need to put HTTPS. Oops. Patience. Okay. This happens in the first lecture. Too eager to show you things quickly. So now I can see that this repository is downloaded. All right. So now I can do a cd, change directory into this repository, HPSC underscore 2023, press enter. And now if I do an ls, it shows two things. One is blue, that means it's a folder. The other is a file called requirements.txt. I can also list the details of these two things. So I can see it's a, so I'll go to cd codes, do an ls minus l, list the contents of the directory. I can also open it in GUI. So I can go to this, go to GitHub, go to HPSC, go to codes and so on. That is also possible. But with experience, you will see that working in command is much quicker than pressing mouse keys. But again, that's convenience, nothing else. And as I said, many a case, when you connect to remote terminals, all you have is access through command only. So then you should definitely know how to use these commands. Any questions till this point? Okay, so now I'll go to a folder called Fortran, because I can see there's a folder called Fortran. And then let's list the contents again. So I can see there's a folder called lecture 1, and that is what I want. So I'll go do a cd lecture 1. By the way, if I type the first few letters and press a tab, it auto completes. That's the reason I'm writing very quickly. It's actually auto completing once I write enough a number of characters to uniquely identify that file or a folder name. So now I am in lecture 1. Now you can see it takes a lot of space with all these details of the directory. So I can change the prompt here. So I can simply say export ps1 is a variable. So now what it does is it simply replaces all this with a dollar space. That's because if I am too deep into a folder structure, then it takes a lot of space and I'm not able to see the commands I write comfortably. Okay. If I do a clear now, all I see is a dollar. Now if I want to see the folder I am in, I do a pwd, that stands for present working directory, and it tells me exactly where I am. pwd. Okay. It's a very important command. There's also a command called who am I. So this is basically the user name in that machine. If you have multiple users, who am I will tell you which user is logged into the machine. Okay, so these this pwd, for example, is also an environment variable. So I can do an echo, and then let's say pwd preceded with a dollar. Dollar is to identify the value of the variable, and then it tells me the complete details. Now I want to store it somewhere, so I'll say lec1 is equal to dollar $pwd. So what it does is the contents of $pwd, which was this complete path, gets stored in a new environment variable called lec1. So I can do an echo. Echo is to see the value of the environment variable, and then dollar lec1. So this is what this environment variable contains. Okay. Now I might be going very quickly, but this is just a demo session, and we are recording these. So in case you want the video recording, we'll give it to you so that you can follow it up later. But this is a demo session. That's the reason I'm going very quickly, just to show you a glimpse of what typically we'll be doing. So now that I'm in this folder, lecture 1, let's see the contents. So there's something called makefile. As I said, we'll be learning about makefiles, but the way they help us is I can now write make, and there's a target called plots in the makefile, which I'll show you in a minute, in a few seconds. So when I say make plots, something happens, but then I do get an error. That happens towards the end, by the way. It says Python. There's nothing like Python here, because if I write Python, it's not even installed here. And what I've done is I've created a virtual environment. We'll be talking about those, how to create them and so on. So we have a virtual environment where you can create or you can have separate environments, virtual environments, and each virtual environment can have different versions of your modules. If you want Python 3.1 in one and you want Python 3.2 in the other, you can have them. So that way is you only activate the module that you want. Okay. So let me go to the desktop. And on desktop, we have something called course-venv. So venv stands for virtual environment. Inside that, you have a folder called venv. So I'll be using this venv folder, the environment that I've created here, to activate that, and that will have the necessary version of Python. So for that, what we do is we say source, and then I give the complete path of the environment. So again, we'll have some session where I'll tell you how to create the environment and how to add different software into it. But for now, this is how we'll activate. So you can see there's a bracket venv that precedes the prompt. So that means I'm inside the environment. I know which environment I'm in. And if I want to deactivate that, I can come out of it. Okay. So let's go back into it. So if I now write Python, something happens. So this Python works now. Okay. Earlier it was not working. So I'll try again, make plots. And this time it runs a bit quickly. And the reason is because it already ran earlier. And as I told you, make is a build system that checks for dependencies. So it had already done most of the work. Only the last step, which was to generate plots using a Python script, that had failed. So it did not repeat the whole complete step, all the steps, because of this dependency checking. All right. So let's see the result first, because typically that is what you want to see first, and then we understand how it works. So now if I do an ls-l, you see these two files called contour.png and pcolor.png. These are the results of your code that you have run. So let's display them. All the PNG files, star.png. And I see that it shows me a contour. And I can, in fact, since I have opened both, I can go to the next one, which is the pseudo color plot of the temperature. So what I have solved here is a problem of heat transfer. Again, no need to go into details for now. So in this problem, we have a rectangular two-dimensional bar. You can think of a plate. The top, this region in the top is in contact with some hot body. So let's say it's boiling water that's in contact with this part, and the rest is all 0. So I'm calling this 1 and this as 0. So I've given some sort of a boundary condition, and you can think of touching two hot bodies on the top and the right in the center, and after some time you'll see this kind of a distribution of temperature in the plate. That's typically solving a heat conduction equation. Those who do not understand it, it's also called a heat diffusion equation, a Laplacian equation, okay, a Laplace's equation or a Poisson equation. So these are the equations that we are solving. So we'll discuss these in the future when we write the algorithms. But for now, what you need to see is that it generates plots. The plots are generated, and we also have a contour plot to see the values. You can see that on the top it's 1, then very far away from these hot boundaries it's close to 0. So it draws these lines of constant temperatures as well. Okay. Any questions? Right. So let's see what's inside a makefile typically. So like Notepad, we have something called Featherpad in this version of Linux. So let's open the file called makefile. Okay, so typically this is how makefile looks. What I want you to focus on this is plots, because we ran this target called plots. I wrote make plots. So what it does is it runs a Python script called plotsolution.py to generate these two plots using the data from the file called solution.txt. So solution.txt is a text file which contains all the temperature data as text. Well, we can check that. So let's open solution.txt. You can see it's got numbers. So it's got the temperatures at different points, and that data is taken and used to plot. So it has x comma y points, and correspondingly it will have a temperature value. That's typically what you want to plot the temperatures, right? So plots needs solution. Now the solution by itself is a target. So this solution.txt target needs an executable to run. So that exe file will run, the code, the Fortran code will run and generate this result data. And that data will then be plotted using Python. But to generate this executable, you need object files. To generate the object files, you need Fortran F90 files. So there's a dependency. If I change something in the middle, it will redo all the steps from that point onwards. So that's what it means by dependency checking. And then we also have a target called clean, which has no dependency. So that basically removes all the .o and .exe files. There's also a target called clobber, which will do a clean, and it will also remove the solution.txt and png files. Okay, so these are the targets. So typically if you open a make file, even if you don't understand how it works, you have an idea of what it is doing. I can even have an intermediate target. I can have a solution.txt as a target. So let's do a make clobber, and now I can see that it's back to the initial stage, just 4 files. Now I can do a make solution.txt, and it will run only to the point where it generates that text file. That's it. By the way, this code, what it is doing is it's running an iterative method to solve for the temperatures in that plate. It does that using one thread, so a serial code. It also runs a parallel version of the code with OpenMP. And you can see that the serial version takes 3.758 seconds, whereas the parallel version took 2.394 seconds. It's not exactly half the time, but there is definitely an improvement. Okay, so this is what we'll be writing. We'll be writing codes from scratch which can do these things, and we'll be seeing the execution times and so on along with the results. Because the aim is to write codes which run faster, right? So we should be able to do some sort of a scaling as to how, if we increase the number of processors or cores, how fast or what is the runtime the code takes. Okay, so now if I do an ls, you can see that the output files are still not there because I did not say make plots. If I do a make plots now it only runs the Python code to generate plots because it had already completed to the step where I had the solution.txt file. Is that clear? Okay. By the way, there is, let's open the, so this is the code that it runs. So what if I make a change to the code? Let's say I do n equal to 119, just a change, and then I save it. So I have changed the code and I have saved it. Now if I do a make plots, what do you think should happen? Anybody? Can I see a raise of hands?
So same plots.
So it will not do anything?
No, sir.
Okay. Anybody else? That is not correct. So let's see. Okay. So it's running the code again. So what it did first was it actually compiled the main code. It ran everything because see, everything was dependent initially on that F90 file which I have changed. So if I change something, I should expect things to happen again. So that is what it did. So we'll learn how it figures out what has been changed. So, okay. So this is very smart, this make file build system. Questions? None? Okay. So let's go back to our PowerPoint. So let me give you a quick summary of what we have done here. So we have this plate which had, I mean, those who have done a CFD course will already know what's happening here. But what we did was we discretized the domain. So rather than finding the temperature everywhere, we decided to find the temperature at discrete points in the grid. So this points labeled from 1 to 16 is where I'll get the values. Of course, I mean, in our case, we had 120 by 120 grid. So we had a lot more points. But to demonstrate that, I've shown only 4 by 4 grid. Okay, so we define, we supply the boundary condition. So we supply the temperature at the boundary. It has some sort of a formula, an update formula that it uses to find the temperatures at each point. So ui comma j, so let's say this u10 is what we're trying to find. It depends on u6, the point below it, u9, the point to the left of it, 11 and 14. This is, I mean, you don't need to know how this equation is obtained, but this is the equation. And you can see that if you write the equation for every point, you'll end up with a linear system of equations. It will be a linear system Ax equal to B. Now you have to invert the A matrix to solve it. But that A matrix, as we'll see in the next lecture, is going to be very sparse. Don't worry about these things. We'll discuss them again next lecture. But this A matrix that we have is very sparse. So this matrix inversion that we might do is going to be very ineffective. We have an even more effective technique called an iterative technique. So what we say is, as at the bottom, the Jacobi method. So what we say is that I'll start with some initial guesses of the temperatures at, let's say, the kth iteration, k equal to 0 in the beginning, and then I'll update the temperatures using this update formula. So u at the first